We will look into two problems in this video. Let the vector field f is given by this one. We need to show that it consists of neither sources nor sinks. That means, we have to show that it is solenoidal, right. So, it suffices to show that the vector field f is solenoidal. Solenoidal means practically there are no sources, no sinks. But on the other hand, a solenoidal vector field is defined like this. If for a vector field the dot product with a grad operator, that means du f, if du f is 0, we say that the vector, we know that the vector field is solenoidal. That means, this is equivalent to this one. If we show that the du f is equal to 0, that implies that the vector field f consists of neither sources nor sinks. So, let us see how we do that. You take du f. So, this is grad operator, this is the vector field, and we did something very similar to this earlier. Now, this one falls into this trap. So, you will end up with this. The second one with the minus sign, you can pull out minus sign here, and y plus z falls into this trap, and the case is the same for the last term. There I have forgotten to put the square bracket. Now, you will end up with this one. Now, let us partially differentiate this. Here it is 1, in this case it is 1, but you have a minus sign here. So, it is minus 1, and this is free of Z, therefore, it is 0. So, you have 0. That means, du f is 0. So, it implies that the vector field is solenoidal, and equivalently you can say that it consists neither sources nor sinks. Okay. All right. So, now we move to the next one. Here a vector field f is given as such. Now, we need to show that we can define a scalar potential or a potential function to this vector field f. So, how can we do that? So, we need to show that it is irrotational. A potential function can be defined only if the vector field is irrotational. How can we do that? Now, we need to show that a vector field being irrotational is equivalent to this one. So, we need to show that curl f is equal to the null vector. So, we need to show that this is equal to 0. So, we take the cross product straight away. The components of the first vector comes in the second line. The components of the second vector come in the third line. Now, we need to evaluate this determinant. So, here we are doing that. So, I times partial y of this one, partial o partial y of this one minus this product. You have it up there. Then minus j times the cofactor of this. So, you eliminate you delete this column and this row containing j. So, these two go hand in hand. So, partial over partial x of this one, you have it up there, minus partial over partial z of this one. So, you have it there. Finally, plus k times this cofactor, right, partial of partial x of this one, you have it there, minus this one, it is here. Now, you simplify. Here this is free of y, therefore, it is 0. The partial over partial y of this one is x, because x is treated as a constant, it is like 2y, the derivative of 2y is 2. Likewise, the derivative of this one is x, when you differentiate, because x is treated as a constant. Similarly, here 2 is a constant. When you differentiate this one partially with respect to z, you will end up with x. With this minus sign, you have minus x. Similarly, you have these two terms and it will be 0, a null vector. That means, okay, since the cross product or the curl F is 0, the vector field is irrotational. A vector field being irrotational implies that you can attach a scalar potential to the vector field. So, in the next video we try to find, we try to determine the potential function once an irrotational vector field is given, right. Okay. Thank you.